Welcome to Good Chemistry with Mrs. Lehman. Hess's law says that regardless of the multiple steps of a reaction, the total enthalpy change, our delta H of the reaction, is equal to the sum of the other changes. So let's talk about some changes that reactions can go through. So here we have a reaction. Nitrogen monoxide reacts with oxygen gas to form nitrogen dioxide. The enthalpy of this reaction is negative 113.2 kilojoules. Now, if we take this same reaction, but we multiply it by 2, so 2 times 2 is 4, 1 times 2 is 2, 2 times 2 is 4, so we have doubled the amount of moles in this reaction. Our enthalpy change will also double. So we'll do 113.2 times 2, and the new enthalpy, this reaction, will release 226.4 kilojoules. Okay, because now in this reaction we have twice as many moles reacting. If we flip the reaction around, so instead of nitrogen monoxide and oxygen gas being our reactants, they're now our products. Well then, instead of 113.2 kilojoules being released, that energy would be absorbed. So we just change the sign. So now we're given this problem. We have carbon reacting with water, so I'm looking at the black reaction, becomes carbon monoxide and hydrogen gas. We want to know the enthalpy of this reaction. However, the only information we're given is the green, purple, and orange reactions. So when carbon reacts with oxygen and produces carbon dioxide, it releases 393.5 kilojoules of energy. When carbon monoxide reacts with oxygen gas to form carbon dioxide, it releases 566 kilojoules of energy. And when hydrogen gas and oxygen react to form water, it releases 483.6 kilojoules of energy. So we need to rearrange these equations to make them look like the black equation. So the way we do this is we start with our first compound. So we have carbon. The only time our single carbon, our solid carbon, shows up is in our first reaction. The carbons in our goal reaction, in the black reaction, and in the green reaction are in the same position. We have 1 mole of each, and they're both reactants. So we're not going to touch that green reaction. Then we're going to move to our next one. So now we have water, H2O, and the only time H2O shows up is in our last reaction, in that orange reaction. But notice, in the black reaction, the water is a reactant, and we have 1 mole of it. In our orange reaction, the water is a product, and we have 2 moles of it. So how do we change this reaction, this orange reaction, to match our black reaction? We would take our orange reaction and multiply it by a negative 1/2. So by multiplying it by a negative, that means we flip the products and reactants. So we would have H2O becoming H2 and O2. By multiplying it by a half, we're multiplying each coefficient by 1/2. So 2 times 1/2 for the H2 is 1. 1 times 1/2 for the O2 is 1/2. And 2 times 1/2 would be 1 H2O. So now, notice the H2O up here and the H2O down here will match. Now what we've done is we have flipped our last reaction and multiplied it by 1/2. So we need to do the exact same thing to our delta H. So now instead of releasing 483.6 kilojoules of energy, this reversed reaction, this flipped reaction, would have to gain that much energy. But we only have half the moles, so our delta H is now 241.8 kilojoules. I have just multiplied the negative 483.6 by negative 1/2 because we're doing the reverse reaction and we have half the amount of moles. Okay, so we've done our carbon and we've done our water. I'm just going to rewrite, I'm going to erase that orange one and rewrite what we have with the brown one. Okay, so let's see what we have. Our next thing is carbon monoxide. So we have CO and we need 1 mole of it on our product side. Here we have CO, but we have 2 moles of it and it's on our reactant side. So again, just like we previously did, we need to multiply this by a negative 1/2. We are flipping the reaction by doing a negative because now instead of releasing 566 kilojoules of energy, we need to gain 566 kilojoules of energy. And then we're dividing the moles in half. So we get carbon dioxide as our reactant now, and it is producing carbon monoxide and oxygen gas. But we have half the moles, so we have only half a mole of carbon dioxide, and we have 1 mole of carbon monoxide, and we have half a mole of oxygen. You do not need to write that one. And I apologize, this reaction was not balanced. So this should have been 2 CO2 because we have 2 carbons now on each side. So, backtracking a little bit, we should have 1 mole of carbon dioxide, not 2. Not 1/2, I'm sorry. So by multiplying our purple reaction by negative 1/2, we have reversed it. So we've switched our reactants with our products, and we have divided the number of moles in half. So now our delta H is going to equal the positive, right? We've reversed it, so instead of releasing energy, it's now absorbing energy. And it's absorbing half that amount of energy because we have half the number of moles. So it's now 283.0 kilojoules. Okay, and let me just rewrite this. Okay, so when we add all of these reactions together, our product side, our reactant side is carbon plus oxygen plus carbon dioxide plus water. Okay, carbon plus oxygen plus carbon dioxide plus water would become carbon dioxide plus carbon monoxide, okay, plus 1/2 oxygen plus 1/2 oxygen. So I'm going to combine those oxygens, and that'll just be 1 oxygen plus H2. And when we look at this reaction, I want you to notice that there is carbon dioxide as a reactant and carbon dioxide as a product, so we can cross those off. There is oxygen as a reactant and oxygen as a product. So what we are left with is carbon plus water becomes carbon monoxide plus hydrogen gas. Carbon plus water becomes carbon monoxide plus hydrogen gas. So we've created our reaction. So now we need to determine what is the enthalpy of the reaction. So all we're going to do is, just like we added each of these equations, we are going to add each of their enthalpies together. So we have negative 393.5 plus 283 plus 241.8, and our delta H of this reaction will be 131.3 kilojoules.